In 1940, a 23-year-old physics student approached the British Air Ministry with an invention. His name was Robert Watson Watt. His invention was radar. The Air Ministry officials listened politely, then dismissed him. "Interesting in theory," they said, "but impractical for military use. Too complex, too expensive, too unreliable. We'll stick with proven methods, thank you." Watson Watt left the meeting discouraged, but not defeated. He continued developing his invention with minimal support. He refined the technology in a small laboratory. He proved it could detect aircraft at distances thought impossible. Within a year, his impractical invention became Britain's secret weapon. By 1940, a network of radar stations covered the British coast. These stations detected incoming German bombers before they reached England. British fighters could intercept raiders with unprecedented accuracy. The Battle of Britain was won partly because of this rejected student invention. German Luftwaffe commanders were baffled. British fighters appeared exactly where they were needed. Every raid was intercepted with suspicious precision. How were the British doing this? German intelligence suspected spies or some breakthrough they hadn't discovered. They never imagined it was the same technology their own scientists had dismissed as impractical. Radar saved Britain. It saved thousands of pilots who could engage enemies efficiently rather than searching blindly. It saved countless civilians who would have died in undetected bombing raids. It changed warfare forever. And it started with a student whose professors and military officials laughed at his theoretical invention. But Watson Watt wasn't the only student inventor mocked for impractical ideas. World War II was full of them. Young engineers, mathematicians and scientists with ideas that seemed absurd, ideas that senior experts rejected as impossible or foolish. Then the impossible ideas worked, and they saved lives, thousands of lives. This is the story of the student inventors who were laughed at, the young minds whose innovations were dismissed by experts, the impractical inventions that became essential weapons, and how desperation forced militaries to listen to ideas they would have rejected in peacetime. Historical context: when orthodoxy meets innovation. Military institutions are inherently conservative. They prefer proven technologies and established tactics. Innovation is viewed with suspicion. Untested ideas are rejected as risky. This conservatism has deep institutional reasons. Military operations require absolute reliability under combat stress. Soldiers' lives depend on equipment functioning exactly as expected. Experimental technology that fails in combat means deaths, missions compromised, battles lost. The military procurement system reinforced this conservatism. Contracts favored established manufacturers with proven track records. Specifications required demonstrable reliability through extensive testing. New technologies faced years of evaluation before military adoption. Better to use older, proven equipment than newer, unreliable equipment. This logic made sense under peacetime conditions. Reliability mattered more than cutting-edge performance. Soldiers needed weapons that worked every time, not weapons that worked brilliantly 90% of the time. But World War II wasn't normal circumstances. The war demanded innovation on unprecedented scales and at unprecedented speeds. Technologies were advancing faster than military institutions could adapt through normal procurement cycles. Young scientists and engineers saw possibilities that experienced military officers couldn't imagine or didn't understand. The generation gap was significant and consequential. Senior military officers in 1939 had learned warfare in World War I or earlier. Their formative military experiences were 20-30 years old. They thought in terms of trenches, cavalry charges, and battleship engagements. Their understanding of technology reflected this background. Radio was new and exotic to many senior officers. Aircraft were still novel weapons requiring special doctrines. Mechanized warfare was controversial and poorly understood. Young scientists and engineers had grown up in a different technological world. They had studied radio, aviation, and modern physics from adolescence. They understood electromagnetic radiation, aerodynamics, quantum mechanics, and nuclear physics. They saw military applications for emerging technologies that older generations couldn't comprehend. This created profound conflict within military research establishments. Young inventors proposed radical innovations based on recent scientific advances. Senior officers dismissed them as impractical fantasies, disconnected from military realities. The inventors were frustrated that good ideas were being ignored due to technological illiteracy. The officers were frustrated by young people who didn't understand operational constraints and military necessity. Both sides had legitimate complaints. Young inventors sometimes proposed ideas that were genuinely impractical given manufacturing capabilities, operational requirements, or resource constraints. Senior officers sometimes rejected good ideas simply because they didn't understand the underlying science and couldn't evaluate feasibility. The challenge facing military research organizations was distinguishing between four categories: innovations that were genuinely impossible with current technology and scientific understanding, innovations that seemed impossible but actually weren't. They just required approaches experts hadn't considered, innovations that were possible but too risky, expensive, or complex for military adoption under current circumstances, innovations that were essential and needed immediate development despite risks and costs. Getting this categorization wrong in either direction had serious consequences. Reject a genuinely revolutionary innovation and you might lose technological advantage, battles, or even the war. Adopt a flawed innovation and you waste critical resources, delay better alternatives, and possibly endanger operations. Britain faced this challenge with particular acuteness in 1939-1940. Germany had demonstrated superior tank forces in Poland and France. The Luftwaffe had shown devastating air power capabilities. Britain needed technological advantages to compensate for numerical and tactical inferiority in conventional forces. This crisis created unprecedented openness to innovation. Ideas that would have been dismissed as impractical fantasy in peacetime got serious consideration. The military establishment was desperate enough to try impossible innovations if they offered potential advantages. Winston Churchill personally championed this shift toward embracing technological innovation. Churchill was 65 years old in 1940, but remarkably receptive to new ideas. He understood that Britain couldn't win through conventional military means alone against Germany's superior forces. Technological innovation was essential not just for advantage, but for survival. Churchill articulated the wizard war concept in speeches and directives. Scientific innovation competing directly with enemy scientific innovation. Whoever developed better technology faster would gain decisive advantages. The nation that mobilized its scientific talent most effectively would ultimately prevail. This philosophy created opportunities for young inventors that would never have existed in peacetime. Ideas that would have languished in research labs for decades got immediate attention and funding. The normal procurement bureaucracy was bypassed for promising innovations. Young scientists found themselves with resources and authority that would have been unthinkable before the war. Several governmental and military research organizations emerged or expanded dramatically. The Telecommunications Research Establishment, TRE, at Malvern, developed radar and related electronic warfare technologies. The Tube Alloys project researched nuclear weapons under conditions of extreme secrecy. MD1, Ministry of Defence 1, nicknamed Churchill's Toy Shop, developed unusual weapons and sabotage devices. Station 9 at Welwyn developed special operations equipment for SOE and resistance movements. The Government Code and Cipher School at Bletchley Park broke enemy codes. These organisations shared common characteristics that distinguished them from traditional military research. They employed hundreds of young scientists and engineers, many in their 20s or early 30s. Many researchers were recent university graduates with cutting-edge training, but minimal practical experience. Some were still students when recruited, their studies interrupted by urgent national need. Very few had military experience or understood traditional military protocols and hierarchies. What these young researchers lacked in experience, they compensated for with fresh thinking and technical expertise. They approached problems without preconceptions about what was possible or impossible. They weren't constrained by decades of "we tried that and it didn't work" thinking. They proposed solutions that seemed absurd to traditionalists who knew such approaches were impossible. Sometimes those absurd solutions actually worked. The organisational culture at places like TRE and Bletchley Park was deliberately unconventional. Dress codes were relaxed. Scientists worked in casual clothes rather than uniforms. Hierarchies were flattened. Junior researchers could challenge senior scientists on technical grounds. Experimentation was encouraged even when failure was likely. Unorthodox approaches were welcomed rather than dismissed. This culture shocked traditionalists, but proved remarkably productive. Innovations emerged rapidly from environments that would have seemed chaotic to conventional military organizations. Young researchers felt empowered to try radical ideas. Senior scientists mentored rather than commanded. The result was creative ferment that produced breakthrough after breakthrough. The most famous example was radar, but there were many others. Young inventors at TRE and related establishments developed proximity fuses that revolutionized anti-aircraft fire effectiveness, the cavity magnetron that enabled powerful, compact radar for aircraft, centimetric radar that could detect submarines and navigate through clouds, window, chaff that confused enemy radar systems, specialized explosives and demolitions for sabotage operations, code-breaking machines, including the bomb and Colossus computers, jet engines that made aircraft far faster than propeller-driven planes, rocket propulsion for missiles and assisted takeoff. Each of these innovations faced initial skepticism from military traditionalists. Each was developed primarily by young engineers and scientists working in the new research organizations. Each was mocked or dismissed by experts before proving essential to military operations. The pattern repeated across all combatant nations, though with different organizational approaches. Germany had young scientists at places like Peenemünde developing V-2 rockets and at BMW developing jet engines. America created the Manhattan Project, employing thousands of young physicists to develop atomic weapons. American university laboratories like MIT's Radiation Lab and Johns Hopkins Applied Physics Lab became innovation centers. The Soviet Union had young designers in Sharashkas, prison laboratories, creating tank and aircraft innovations. Japan had young engineers developing long-range submarines, suicide weapons, and aircraft carriers. Youth provided specific advantages that experience couldn't match in this context. Young minds hadn't learned what was impossible. They hadn't internalized decades of failed attempts at certain approaches. They hadn't spent careers building expertise in established technologies that might soon be obsolete. They were willing to try approaches that experienced engineers knew wouldn't work, except sometimes they did work with new materials or techniques. They had recent training in cutting-edge science that older engineers hadn't studied. But youth also created significant disadvantages that couldn't be ignored. Young inventors sometimes lacked practical knowledge about manufacturing processes and production realities. They proposed solutions that were theoretically sound, but impossible to mass-produce with existing industrial capabilities. They didn't always understand military operational requirements. They designed elegant solutions to problems that didn't actually matter operationally. They sometimes underestimated practical constraints like maintenance requirements, logistics, training needs, or combat robustness. The most effective innovations came from structured collaboration between different generations and expertise levels. Young inventors providing creative solutions and scientific foundation. Experienced engineers ensuring those solutions were practically manufacturable and maintainable. Military officers ensuring the technology actually met operational needs and would function in combat conditions. Production specialists ensuring the innovation could be manufactured at scale with available resources. When this collaboration worked effectively, the results were remarkable. When it failed, when any group dominated without input from others, resources were often wasted on impractical projects. Britain's radar development exemplified successful collaboration. Watson Watt provided the theoretical foundation and initial proof of concept. Experienced engineers like E.G. Bowen solved practical implementation problems with transmitters, receivers, and displays. RAF officers like Hugh Dowding ensured the system met operational requirements for fighter command. Industrial partners like EMI and Plessey developed manufacturing processes for mass production. The result was a deployed operational radar network by 1940, remarkably fast development for such complex technology. Other projects exemplified collaboration failure and wasted resources. Britain's Great Panjandrum was a rocket-propelled wheel designed to breach Atlantic Wall fortifications. The concept seemed promising in theory: roll explosives against fortifications. Young inventors designed an ingenious propulsion system, but they didn't adequately consider practical issues like controllability and reliability. In practice, the device was wildly uncontrollable and dangerous to its operators. Test demonstrations became comedy as the wheel careened unpredictably, terrifying observers. It was abandoned after several spectacular failures that wasted resources and time. The difference between radar, success, and Panjandrum, failure, wasn't primarily the technology itself. It was whether young innovation was properly integrated with practical engineering wisdom and military operational requirements. Radar had this integration. Panjandrum didn't. World War II forced military institutions to become dramatically more receptive to young inventors than they had ever been. Desperation overcame institutional conservatism. Ideas that would have been automatically dismissed in peacetime got serious consideration and development funding. Student inventors got opportunities and responsibilities they would never have received in normal circumstances. Many innovations failed spectacularly. Resources were wasted on projects that didn't work. Some young inventors proved unable to deliver on their promises, but some innovations succeeded spectacularly. And those successes saved thousands of lives, changed the course of battles, and arguably determined the war's outcome. The lesson was clear but difficult for traditional institutions to internalize. Youth sometimes provides advantages that experience cannot match. Impossible-seeming ideas sometimes work. Listening to dismissed students sometimes leads to breakthrough innovations that change everything. Technical analysis, the innovations that seemed impossible. Radar technology development shows how student innovation overcame expert skepticism. The fundamental principle was understood before the war. Radio waves reflect off metal objects. By detecting these reflections, you can locate objects remotely. But turning this principle into a working military system seemed impossible to most experts. The technical challenges were enormous. First challenge: generating powerful enough radio waves. Early radio transmitters were weak. Their signals scattered and dissipated quickly. Detecting reflections from aircraft dozens of miles away seemed impossible. Watt and his team solved this by developing powerful pulse transmitters. Instead of continuous weak transmission, they sent short, powerful pulses. The pulses had enough energy to reflect detectably from distant aircraft. Between pulses, the receiver listened for echoes. This solution seems obvious now. But in 1935, it was radical. Existing radio technology used continuous transmission. Pulse transmission required entirely new circuit designs. Second challenge: detecting extremely weak return signals. The radio wave, travelling to the aircraft and back, loses 99.9999% of its energy. The echo is extraordinarily faint. Detecting it amid electrical noise seemed impossible. The solution was sensitive receivers with precise tuning. Student engineers developed amplifier circuits with unprecedented sensitivity. They used emerging vacuum tube technology in innovative configurations. They filtered out noise frequencies that didn't match the transmitted pulse. Again, this seems straightforward in retrospect, but in 1935, it required pushing vacuum tube technology beyond what experts thought possible. Third challenge: determining distance to detected aircraft. Detecting that an aircraft exists isn't enough. You need to know how far away it is. Otherwise, you can't intercept it. The solution was measuring the time between pulse transmission and echo reception. Radio waves travel at the speed of light, 300,000 kilometers per second. Measure the delay time, calculate the distance. But this required measuring delays of microseconds with 1930s technology. Electronic timing circuits that precise didn't exist. Young engineers had to invent them. They developed oscilloscope displays that showed pulses and echoes visually. Operators could measure the distance between transmitted pulse and echo on the screen. This distance corresponded to range to the target aircraft. Fourth challenge: determining direction to detected aircraft. Knowing distance isn't enough. You need to know which direction the aircraft is. Otherwise, you know an aircraft is 30 miles away, but not which 30 miles. The solution was directional antennas. Antennas that transmitted and received preferentially in one direction. By pointing the antenna and detecting strongest signal, you could determine direction. Rotating the antenna and tracking signal strength gave precise bearing. Combined with range from pulse timing, you had aircraft position. But antenna design for radar frequencies was itself a significant challenge. Conventional radio antennas were designed for much lower frequencies. Radar operated at megahertz to gigahertz frequencies. Antenna behavior at these frequencies wasn't well understood in 1935. Young engineers experimented with various designs. Dipole antennas arranged in arrays, parabolic reflectors that focused radio waves like satellite dishes, corner reflectors that enhanced signal in specific directions. Each design had advantages and disadvantages. Arrays were complex, but provided excellent directional control. Parabolic reflectors were simple, but required precise manufacturing. Corner reflectors were cheap, but had limited directionality. The final chain-home radar system used imposing steel towers. Transmit towers were 360 feet tall, taller than most buildings of the era. Receive towers were 240 feet tall. These massive structures were visible for miles and difficult to disguise. But they worked. The antennas could detect aircraft at ranges exceeding 100 miles. They could determine bearing to within a few degrees. Combined with range measurement, they provided position accurate enough for fighter interception. These solutions required innovations in multiple engineering disciplines, high-power radio frequency engineering that barely existed as a field in 1935, sensitive receiver design pushing vacuum tube technology to its limits, precision timing circuits measuring microseconds when most clocks measured seconds, antenna engineering at frequencies where conventional designs didn't work, signal processing techniques that would later become the foundation of modern electronics. Every component pushed existing technology beyond what experts thought possible. Senior engineers reviewed early radar proposals and declared them unworkable. The transmitters would be too weak to detect echoes from distant targets. The receivers would be too insensitive to detect signals buried in electrical noise. The timing would be too imprecise to measure microsecond delays accurately. The antennas would be too inefficient to provide useful range and directional information. But young engineers proved the experts wrong through systematic experimentation and innovation. They didn't know it was impossible, so they approached each challenge assuming a solution existed. They tried approaches that conventional wisdom said wouldn't work. They iterated designs rapidly, learning from failures. By 1938, working radar stations were detecting aircraft at ranges over 100 miles. This was thought completely impossible just 3 years earlier. The theoretical physicists said the physics worked, but practical implementation was impossible. The practical engineers said the engineering was impossible with current technology. Both were proven wrong by young engineers who didn't accept impossibility. The cavity magnetron development exemplifies similar patterns of overcoming expert skepticism. This device generated powerful microwave radiation, essential for compact airborne radar. Before the cavity magnetron, radar required huge ground stations with massive equipment. The transmitters weighed tons and consumed enormous electrical power. They required dedicated power plants to operate. Aircraft couldn't carry radar equipment. It was far too large, heavy, and power-hungry. This seemed like a fundamental limitation. Powerful radio frequency generation required large vacuum tubes and massive power supplies. Scaling down seemed impossible without proportionally reducing power output, and reduced power meant reduced range, making the radar useless. Young physicist John Randall and engineer Harry Boot approached this challenge at the University of Birmingham in 1940. They were 28 and 27 years old, respectively. Neither had extensive experience in microwave engineering. It was a nascent field. Neither had published significant research papers or established professional reputations. Their supervisor, Professor Mark Oliphant, challenged them with what seemed an impossible requirement: generate kilowatts of power at gigahertz frequencies. Do it in a device small enough to fit in an aircraft. Do it efficiently enough to run on aircraft electrical systems. Existing technology produced milliwatts at gigahertz frequencies. Scaling from milliwatts to kilowatts, a million-fold increase, seemed utterly impossible. Every expert Oliphant consulted said it couldn't be done with any foreseeable technology. Randall and Boot approached the problem with fresh eyes unburdened by expert knowledge of why it couldn't work. They weren't experts in the field. They didn't know what had been tried and failed. This ignorance paradoxically became an advantage. They studied the physics of electron behavior in magnetic fields. They realized that electrons could be made to circulate in resonant cavities. This circulation could induce electromagnetic oscillations at the cavity's resonant frequency. By designing cavities that resonated at microwave frequencies, they could generate microwave radiation. The concept was theoretically sound, but had never been demonstrated practically. Many experts doubted it could work at the required power levels. The electron currents needed would be enormous. The magnetic fields would need to be precisely controlled. Manufacturing the resonant cavities with required precision seemed impossible. Randall and Boot worked intensively for weeks in early 1940. They built dozens of experimental designs with different cavity configurations. Most failed completely, producing nothing useful. Some failed spectacularly, with explosions, melting, or electrical arcs. They documented each failure and modified designs iteratively. They were essentially inventing microwave engineering as a discipline. Each failed experiment taught them something about how electrons behaved at these power levels and frequencies. On February 21, 1940, they achieved a breakthrough. Their cavity magnetron produced 400 watts at 3 gigahertz. This was orders of magnitude better than anything previously achieved. It was instantaneously obvious that they had achieved something revolutionary. The device was compact, about the size of a large fist. It could be powered by aircraft electrical systems. It produced enough power for effective airborne radar. Senior engineers who examined the device were initially skeptical. They insisted on independent testing to verify the claims. The performance seemed too good to be believed. How could two young, inexperienced researchers achieve what entire laboratories had failed to do? But repeated testing confirmed the results. The cavity magnetron worked exactly as Randall and Boot claimed. Refined versions quickly produced multiple kilowatts. Production models were soon generating 10 kilowatts or more. The impact was immediate and transformative. The British Tizard mission carried cavity magnetron technology to America in September 1940. This was one of the most significant technology transfers in history. American officials were stunned when they saw the performance. One American scientist, Dr. Alfred Loomis, examined the device and immediately recognized its significance. He called it the most valuable cargo ever brought to our shores. The cavity magnetron was worth more strategically than shiploads of gold. Within months, American industrial capability was mobilized to mass-produce cavity magnetrons. MIT's radiation laboratory was established specifically to develop radar applications. Thousands of engineers and scientists worked on magnetron-based radar systems. The cavity magnetron enabled multiple critical applications: airborne interception radar for night fighters that could detect enemy bombers in darkness, H-2S navigation radar that allowed bombers to navigate accurately at night and through clouds, ASV, air-to-surface vessel, radar that enabled anti-submarine aircraft to detect surfaced U-boats, gun-laying radar that allowed anti-aircraft batteries to engage targets precisely at night, proximity fuses that used miniature radar to detect nearby targets. Each of these applications saved lives and improved military effectiveness significantly. Night fighters could intercept enemy bombers that had previously operated with impunity in darkness. Bombers could navigate accurately to targets without visual references, improving bombing effectiveness. Patrol aircraft could detect submarines attempting to surface and recharge batteries, reducing U-boat effectiveness. Anti-aircraft guns could engage night raiders precisely rather than firing blindly into darkness. Randall and Boot had been unknown PhD students before February 1940. Their invention changed warfare and saved thousands of lives. Military experts who had initially dismissed the cavity magnetron as impossible had to acknowledge that impossible had been achieved. After the war, neither Randall nor Boot achieved great public fame despite their contribution. Boot became a university professor, teaching physics. Randall became a university administrator. Both lived quiet, productive academic lives. They rarely discussed their wartime work with students or colleagues. When occasionally asked about the cavity magnetron, Boot would deflect attention. "We were young and didn't know it was impossible. So we just tried things until something worked. Looking back, I'm amazed it worked at all. We were very lucky." This extreme modesty understates their revolutionary achievement. They had taken a problem that every expert said was impossible. They had solved it through innovative thinking and persistent experimentation. Their luck was actually brilliance, combined with willingness to try approaches experts had ruled out. The pattern repeats across these student innovations. Experts said it was impossible. Students didn't know enough to believe the experts. Students tried anyway. The impossible became possible. Lives were saved. Barnes-Wallis's bouncing bomb exemplifies another pattern. Wallis was an aircraft designer in his 50s, not a student, but treated like one by military officials. His idea seemed absurd to everyone who heard it. The problem, Germany's Ruhr dams provided water and hydroelectric power to German industry. Destroying the dams would cripple German industrial production. But the dams were massive concrete structures. Conventional bombing couldn't destroy them. Torpedoes might work, but the dams had anti-torpedo nets. Conventional bombs weren't heavy enough to breach the dam walls. Heavy bombs dropped from high altitude were too inaccurate to hit the dams. Wallis proposed a revolutionary solution, the bouncing bomb. A cylindrical bomb, spinning backwards, dropped from low altitude. The bomb would skip across the water surface like a stone. It would bounce over the anti-torpedo nets. When it hit the dam wall, it would sink alongside the wall. It would detonate at depth, creating a shock wave that would breach the dam. Every military expert who heard this idea thought Wallis was insane. Bombs don't bounce. The idea violated everything they knew about ballistics. It was ridiculed and rejected repeatedly. But Wallis had done the mathematics. He had calculated the physics. He knew the bomb would work if designed correctly. He tested scale models in his garden. The models bounced exactly as predicted. He filmed the tests and showed them to military officials. They remained skeptical but authorized limited development. The full-scale bomb worked. On May 16–17, 1943, RAF bombers attacked the Ruhr dams. The bouncing bombs breached 2 major dams and damaged a third. Flooding destroyed German factories and infrastructure. An impossible idea conceived by an older engineer treated like a foolish student became a decisive weapon. The proximity fuse exemplifies American student innovation. Before proximity fuses, anti-aircraft shells used timed fuses. Gunners had to estimate target altitude and set fuses accordingly. If the estimate was wrong, shells exploded too high or too low. Accuracy was poor. Thousands of shells to bring down one aircraft. A proximity fuse would detonate automatically when near the target. No estimation needed. The shell would know when it was close enough. The problem, creating a reliable fuse that could survive being fired from a gun. The acceleration was 20,000 Gs. This would destroy any conventional electronic device. Young engineers at Johns Hopkins University Applied Physics Laboratory developed the solution. They miniaturized vacuum tubes to withstand extreme acceleration. They created radio circuits that detected proximity to metal objects. They designed the entire system to activate only after leaving the gun barrel. The VT fuse, variable time fuse, though everyone called it proximity fuse, revolutionized anti-aircraft defense. Effectiveness increased from 2% hits to over 50% hits. This was the difference between acceptable losses and decimated bomber formations. The fuse was so effective that it was classified above top secret. It was only used over water where duds couldn't be recovered by the enemy. Later, it was used in the Battle of the Bulge, where its effectiveness against ground targets shocked German forces. Student engineers at a university laboratory had created a weapon that changed warfare. Senior military officers had initially dismissed proximity fuses as too complex and fragile. The students proved them wrong. The Colossus computer for code breaking exemplifies how young mathematicians achieved the impossible. German Enigma codes seemed unbreakable. The number of possible settings was astronomical. Testing every possibility would take longer than the age of the universe. Young mathematician Alan Turing and others developed mathematical techniques to reduce the search space. But even with clever mathematics, the calculations were overwhelming. Human calculators couldn't work fast enough. The solution was automation. Build a machine to do the calculations. This required electronic computation on a scale never attempted. Tommy Flowers, a 35-year-old post office engineer, designed Colossus, the first electronic programmable computer. It used 1/1500 vacuum tubes, far more than anyone thought could work reliably. Senior engineers said a machine with that many tubes would never function. Tubes failed constantly, they argued. The machine would break down continuously. Flowers proved them wrong. He designed the circuitry to minimize tube failures. Colossus worked reliably for hours at a time. It cracked German codes that humans couldn't break. The intelligence gained from Colossus shortened the war. Historians estimate it saved hundreds of thousands of lives. It was built by a young engineer who ignored experts saying it was impossible. A pattern emerges from these examples. Young inventors proposed solutions that experts said wouldn't work. The inventors tested their ideas anyway. The ideas worked. The innovations saved lives and changed warfare. The common factor wasn't that young inventors were smarter. It was that they were less constrained by conventional thinking. They hadn't learned what was impossible yet. So they tried impossible things, and discovered some impossible things were actually possible. Human impact. The students who changed history. Robert Watson Watt was 42 when he demonstrated practical radar in 1935, but he started working on radio direction finding as a young meteorologist in his 20s. His early papers on using radio waves to locate thunderstorms were dismissed as impractical. Interesting theoretical work, his professors said, but no practical applications. Focus on conventional meteorology, young man. Watson Watt ignored this advice. He continued researching radio detection through the 1920s and early 1930s. His work was poorly funded and largely ignored. In 1935, the British government asked if radio waves could create a death ray to destroy enemy aircraft. Watson Watt calculated that this was impossible, but he realized radio waves could detect aircraft even if they couldn't destroy them. He wrote a memo titled Detection of Aircraft by Radio Methods. He described how pulsed radio transmitters could detect aircraft at long ranges. He estimated ranges of 50-plus miles were achievable. Air Ministry officials were skeptical. The concept seemed far-fetched. But Britain was desperate for air defence innovations. They authorised a small demonstration. On February 26, 1935, Watson Watt demonstrated radio detection of aircraft. A small transmitter detected a bomber at 8 miles range. The demonstration was crude but conclusive. The principle worked. The Air Ministry immediately classified the work as secret. They provided funding for full development. Within a year, prototype radar stations were operating. By 1938, a chain of radar stations covered Britain's coast. The Battle of Britain in 1940 vindicated Watson Watt's decade of dismissed research. British fighters were vectored precisely to intercept German raiders. The Luftwaffe couldn't understand how the British achieved such precise interception. German pilots reported that British fighters appeared as if they knew we were coming. They did. Radar told them exactly where German formations were. Watt was knighted in 1942 for his contributions. The young meteorologist, whose work was dismissed as impractical, had saved Britain. John Randall and Harry Boot were young PhD students when they invented the cavity magnetron. Randall was 28, Boot was 27. Neither had published significant papers. Neither had reputations or established expertise. They worked at the University of Birmingham under Professor Mark Oliphant. Oliphant challenged them to develop a powerful microwave source. The requirement seemed impossible. Kilowatts of power at gigahertz frequencies in a package small enough for aircraft. Existing technology produced milliwatts at best. Scaling to kilowatts seemed to require enormous, impractical devices. Randall and Boot approached the problem with fresh eyes. They weren't experts in microwave engineering. They didn't know what had been tried and failed. This ignorance was an advantage. They worked intensively for weeks. They built dozens of experimental designs. Most failed. Some failed spectacularly, exploding or melting. On February 21, 1940, they achieved success. Their cavity magnetron produced 400 watts at 3 GHz. This was orders of magnitude better than anything previously achieved. The impact was immediate and enormous. The British Tizard mission took cavity magnetron technology to America in 1940. American officials were stunned by the performance. One American scientist called it the most valuable cargo ever brought to our shores. The cavity magnetron enabled airborne radar for night fighters, navigation radar for bombers, anti-submarine radar for patrol aircraft, gun-laying radar for anti-aircraft batteries. Each of these applications saved lives. Night fighters could intercept enemy bombers in darkness. Bombers could navigate accurately without visual references. Patrol aircraft could detect submarines before they submerged. Anti-aircraft guns could engage targets precisely. Randall and Boot had been unknown PhD students. Their invention changed warfare and saved thousands of lives. After the war, neither achieved great fame. Boot became a university professor. Randall became a university administrator. Both lived quiet, productive lives. They rarely discussed their wartime work. When asked about the cavity magnetron, Boot would say, "We were young and didn't know it was impossible, so we just tried things until something worked. Looking back, I'm amazed it worked at all. We were very lucky." This modesty understates their achievement. They had taken an impossible problem and solved it through innovation and persistence. Their luck was actually brilliance applied to a problem experts had given up on. Joan Clark was a 20-year-old mathematics student at Cambridge when World War II began. She was recruited to Bletchley Park to work on code breaking. As a woman, she was paid less than male colleagues doing identical work. Her official title was linguist, because women couldn't officially be cryptanalysts. Despite this discrimination, Clark became one of the most effective code breakers at Bletchley Park. She worked closely with Alan Turing on breaking German naval Enigma codes. These were the most difficult Enigma variants. Clark developed mathematical techniques that dramatically reduced decryption time. Her methods were incorporated into the bomber machines that automated code breaking. One particular technique she developed saved an estimated 2,000 Allied merchant seamen's lives. By cracking naval Enigma more quickly, convoy routes could be adjusted to avoid U-boat patrol lines. Fewer ships were sunk. Fewer sailors died. Clark received little recognition during or immediately after the war. She was paid a fraction of what male cryptanalysts earned. She received no public honours. Her work remained classified for decades. In a 1970s interview, after her work was partially declassified, she reflected, "They dismissed me as just a girl who was good at puzzles. The senior cryptanalysts didn't take me seriously at first, but mathematics doesn't care about gender. Either your method works or it doesn't. Mine worked. Eventually, they had to accept that." She died in 1996. Only in recent years has her contribution been properly recognized. Her story exemplifies how student innovation was dismissed not just for being young, but for coming from those society undervalued. These personal stories reveal the human reality behind technical innovation. These weren't abstract geniuses working in isolation. They were young people facing skepticism, discrimination, and doubt. They persevered because they believed their ideas would work. They were proven right, and their persistence saved thousands of lives. Strategic impact: how student innovations changed the war. The strategic impact of radar alone justifies examining student innovation in Wabiyobu. Britain's radar network provided early warning that was essential for survival. Without radar, British fighters would have scrambled randomly. They would have searched blindly for German bombers. Most would have missed the enemy entirely. German raids would have succeeded unchallenged. The numbers demonstrate radar's impact. During the Battle of Britain, July-October 1940, German flew approximately 1,980 bomber sorties. British fighters intercepted about 1,300 of these, 70% interception rate. Without radar, interception rates would have been under 20%. This means radar enabled interception of an additional 940 bomber sorties. Each intercepted sortie meant bombs that didn't fall on British cities. It meant German bombers forced to abort missions or sustain losses. It meant preserved British industrial capacity and morale. The RAF lost about 1,000 fighters during the Battle of Britain. German losses were approximately 1,980 aircraft. This 1:1.9 exchange ratio was sustainable for Britain. Without radar, the exchange ratio would have been much worse. British fighters would have exhausted fuel searching for enemies. German bombers would have completed missions with minimal opposition. British fighter losses would have been higher relative to German losses. An unfavourable exchange ratio would have meant RAF defeat. RAF defeat would have meant German air superiority. Air superiority would have enabled German invasion. Radar, invented by a student who was initially dismissed, prevented German invasion of Britain. This is not hyperbole. Multiple historians have concluded radar was essential for British survival in 1940. The cavity magnetron's strategic impact extended beyond Britain. Airborne radar enabled night interception of German bombers. Before airborne radar, night bombing was nearly impossible to stop. Bombers could operate with impunity in darkness. The introduction of radar-equipped night fighters changed this. German bomber losses at night increased dramatically. The Luftwaffe was forced to reduce night operations. British cities experienced less bombing damage. The strategic bombing campaign against Germany also relied on cavity magnetron technology. H2S radar allowed bombers to navigate and identify targets at night and through clouds. Without this, the bomber offensive would have been far less effective. The proximity fuse's strategic impact is measurable. V-1 flying bombs attacked Britain in 1944-1945. These cruise missiles were difficult to intercept with conventional anti-aircraft fire, but proximity-fused shells dramatically improved success rates. Anti-aircraft batteries using VT fuses destroyed about 80% of V-1s. Batteries using conventional fuses destroyed about 25%. This difference meant fewer V-1s reaching London, fewer casualties from V-1 impacts, reduced terror and disruption to British war effort. In ground combat, VT fuses revolutionized artillery effectiveness. Artillery equipped with proximity fuses was 3 to 5 times more lethal against infantry. German forces in the Battle of the Bulge reported that American artillery with super fuses was devastating. Colossus and code breaking had enormous strategic impact. Breaking German codes provided intelligence that influenced naval convoy routing to avoid U-boats, Allied invasion planning based on German dispositions, deception operations that misled German intelligence, tactical decisions informed by knowledge of German intentions. Historians debate exactly how much code breaking shortened the war. Estimates range from 6 months to 2 years. Even the conservative estimate of 6 months represents hundreds of thousands of lives saved. The cumulative strategic impact of student innovations was decisive. These weren't marginal improvements. They were force multipliers that fundamentally changed operational capability. Consider a counterfactual. World War II without these student innovations. No radar. German invasion of Britain likely succeeds, or Britain is bombed into submission. No cavity magnetron. Night bombing cannot be countered effectively. Strategic bombing is far less effective. No proximity fuse. V1 defences are inadequate. Artillery is far less effective. No code-breaking computers. Vital intelligence is unavailable. Operations are less informed. In this counterfactual world, the Allies likely still win eventually. American industrial might and Soviet manpower would eventually prevail, but the war would have lasted years longer. Casualties would have been far higher. The destruction would have been more extensive. Student innovations didn't win the war alone, but they shortened it and reduced casualties substantially. They turned potential Allied defeat in 1940 into eventual victory. Modern relevance. Why we still dismiss young innovators. The pattern of dismissing student innovation continues today. Young engineers and scientists propose radical solutions. Experienced experts dismiss them as impractical. Sometimes the experts are right. Sometimes they're wrong. Silicon Valley's culture explicitly valorizes young innovation over experience. Companies are founded by college dropouts. Billion-dollar businesses are built by people in their 20s. The technology sector learned W. Dupuis' lesson. Youth provides advantages that experience can't match, but other sectors remain skeptical of young innovators. Traditional industries prefer experienced professionals. Government bureaucracies favor established procedures over innovation. Military organizations remain conservative about unproven technologies. This creates the same dynamic that Wabiyubui exposed. Good ideas are dismissed because they come from young, inexperienced sources. Experts are confident that impossibility they've internalized is real rather than learned. Modern examples: parallel, Babiyuwen Titun stories. SpaceX proposed reusable rockets, experts said impossible. Tesla proposed mass-market electric vehicles, experts said impractical. DeepMind proposed artificial intelligence could master complex games, experts said decades away. In each case, young engineers achieved what experienced experts declared impossible. The pattern repeats because the underlying psychology hasn't changed. Experience teaches what doesn't work, but sometimes doesn't work means didn't work with the technology and approaches we tried 20 years ago. Technology advances. New approaches become possible. But experienced experts still think in terms of old limitations. Young innovators haven't learned those limitations yet. They approach problems assuming solutions exist. They try approaches experienced engineers know won't work. Sometimes they fail. Sometimes they succeed and prove the experts wrong. The challenge for organizations is creating environments where both experience and innovation are valued. Experience prevents wasteful repetition of known failures. Innovation discovers that some known failures aren't failures anymore. WN research organizations like TRE succeeded by combining young innovation with experienced oversight. Young scientists proposed radical ideas. Experienced engineers evaluated feasibility. Military officers ensured operational relevance. This three-way collaboration filtered out impractical ideas while allowing good ideas to flourish. Modern organizations need similar structures. Pure innovation without experience leads to wasteful failures. Pure experience without innovation leads to stagnation. The modern military still struggles with this balance. Defense procurement favors established contractors. Innovative startups struggle to enter defense markets. Regulations designed to prevent waste also prevent innovation. But there are positive examples. DARPA deliberately seeks high-risk, high-reward innovations. They fund young researchers working on ideas that seem impossible. Many projects fail. But successes like the Internet, GPS, and stealth technology justify the approach. The lesson from W2B Student Innovations is clear. Don't dismiss ideas just because they seem impossible. Don't dismiss inventors just because they're young or lack credentials. Evaluate ideas on merit, not on the authority of the person proposing them. This is difficult in practice. Human psychology naturally defers to authority and experience. Challenging established experts feels uncomfortable. Defending ideas against skeptics requires confidence young people often lack. Creating cultures where young innovators can challenge orthodoxy requires deliberate effort. It requires valuing ideas over credentials. It requires protecting young innovators from dismissive skepticism. It requires giving them resources to prove their ideas. But the payoff can be enormous. Watt's radar saved Britain. Randall and Boot's cavity magnetron changed warfare. Turing and Clark's code breaking shortened the war. These innovations came from young people whose ideas were initially dismissed. Imagine what innovations we're currently dismissing. Imagine what problems could be solved if we listened to impractical ideas from inexperienced sources. WE taught that survival sometimes depends on listening to those we'd normally dismiss. We should remember that lesson. Conclusion. The students who saved the world. They were laughed at. Their ideas were dismissed as impractical, theoretical, impossible. Their youth and inexperience were held against them. Senior experts knew better. Robert Watt's radar couldn't possibly work. John Randall and Harry Boot's magnetron violated known limitations. Barnes-Wallace's bouncing bomb defied physics. Proximity fuses were too complex and fragile. Electronic computers with 1/500 vacuum tubes would never function reliably. Except they all worked, and they saved thousands of lives. The pattern was consistent across all these innovations. Young inventors proposed radical solutions to critical problems. Experienced experts dismissed the solutions as impossible. The inventors built prototypes anyway. The prototypes worked. The innovations became essential weapons. The skepticism wasn't entirely wrong. Many impossible ideas truly were impossible. Student inventors proposed plenty of ideas that failed. Experience was right to be skeptical of unproven technologies. But experience was also wrong often enough to matter. The impossible ideas that worked changed the war. They turned potential defeat into victory. They saved nations and lives. Watt's radar prevented German invasion of Britain. Without it, Britain might have fallen in 1940. The entire course of the war would have changed. The cavity magnetron enabled technologies that were essential for Allied victory: night fighters, navigation radar, anti-submarine warfare. Each application saved lives and improved military effectiveness. Proximity fuses increased anti-aircraft effectiveness 5-fold. This meant bombers that survived to complete missions, crews that returned home instead of dying. Code-breaking computers provided intelligence that shortened the war. Every month the war ended earlier saved tens of thousands of lives. These weren't marginal improvements. These were decisive innovations that changed strategic balance. And they came from students and young engineers, people who didn't know what was impossible, people who tried things experts knew wouldn't work, people who proved the experts wrong. The lesson is uncomfortable for societies that value experience and credentials. We want expertise to matter. We want years of study and practice to confer wisdom. We want to believe that young people need to learn from their elders before contributing. But World War II proved this isn't always true. Sometimes youth is an advantage. Fresh perspectives see solutions that experience misses. Lack of preconceptions enables approaches that experts have ruled out. This doesn't mean experience is worthless. Most student ideas that seem impossible actually are impossible. Experience prevents wasteful pursuit of dead ends. Expertise remains valuable and necessary, but experience becomes dangerous when it closes minds to possibilities. When "we tried that and it didn't work" becomes "it can never work." When "I've never seen it done" becomes "it can't be done." When "you're too young to understand" becomes "your idea doesn't deserve consideration." 121 forced military organizations to overcome this closed-mindedness. Desperation made them listen to dismiss students. Survival required trying impractical ideas. They discovered that some impractical ideas were actually breakthrough innovations. The students they had laughed at saved their nations. Modern institutions should learn this lesson without requiring existential crisis to force it. Listen to young innovators even when they seem impractical. Evaluate ideas on merit, not the credentials of the proposer. Create space for radical innovations alongside incremental improvements. This is difficult. It requires humility from experts. It requires patience with young people who don't understand why their ideas won't work. It requires accepting that many attempts will fail. But the potential rewards justify the difficulty. The next Watson Watt might be a student somewhere right now, proposing an idea that seems impossible, being dismissed by experts who know better. If we listen, we might discover another innovation that changes the world. If we dismiss them, we might miss the solution to problems we think are unsolvable. But Dewey proved that impossible ideas sometimes work, that students sometimes know more than experts, that youth sometimes sees what experience misses. The question is whether we've learned that lesson, or whether we're still dismissing the students whose inventions might save thousands. The laughter stopped when radar saved Britain, when the cavity magnetron enabled airborne radar, when proximity fuses stopped V1 attacks, when code breaking shortened the war. The experts who had dismissed these student inventions were proven wrong, dramatically, decisively, historically wrong. We should remember their mistake and avoid repeating it, because somewhere, right now, a student has an idea that seems impossible, an idea that experts will dismiss, an idea that might save thousands of lives. Will we laugh or will we listen? The students who were laughed at during Wabiupain saved the world. Their inventions prevented defeat, enabled victory, and preserved freedom. We owe them more than gratitude. We owe them the lesson of their experience. Don't dismiss the impossible. Don't laugh at the impractical. Don't ignore the young innovators, because sometimes the student who seems foolish is actually the genius who will save us all. Dawu Tutus proved it. The radar that saved Britain, the magnetron that enabled modern warfare, the proximity fuse that stopped cruise missiles, the computers that broke unbreakable codes, all invented by students, all dismissed as impossible, all proven essential. They laughed at the student inventions, until those inventions saved 1,000 pilots and countless others. The laughter stopped, the gratitude began, and the lesson remains. Listen to the young innovators, even when they seem impractical, especially when they seem impossible, because impossible is just a word, and students often prove it wrong, 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 often prove it wrong.